future students, here we go on to the proof of order. It's going to be recording. I think we're all set. Got most of it. It's horrible marker, but too much. Yesterday, with your help, I invented a new metaphor for the task of mathematical proof. And I wanted to reprise that briefly before we jump into this. I want you to have some context in mind. I want you to have some clear thoughts in your head as to what we're attempting today, because it does feel, in my experience, it feels different to students from the kind of typical math class experience. I asked you the fundamental question, like, how do you answer a question? What are the ways that you can answer a why question? So if you imagine, for each of you, imagine that you are responsible for a young person, like a 3, 4, 5-year-old. And in that situation, everyone who's got Chromebooks or laptops open, if you'll close them, I really want, take some good notes. The notes are going to start coming quick and heavy. There's this setup, but once we get through this, it'll come back. And it will likely go, last period, it went with 8 seconds left at the end of the period. Doesn't look like I need to give this notice, but one of the things that I said to my last period is, knowing that there's 24 points on the other side of really understanding this lesson, maybe it's a good time to go into the hallway, do some jumping jacks, get that blood flowing in your brain. You don't want early morning kind of sluggishness to keep you from capturing as much as possible out of what we're doing today. Okay, so you're all imagining this scenario. You're responsible for a young person. And the young person is up. And it's time for the young person to go to bed. And you say to the young person, it's time to go to bed. And that young person looks at you and says, why? What choices do you have to respond to that? What are the kind of 3 ways that you can respond to them? There's 3, and I guess, depending where we're going to go on this, there's really 4 kind of ways. The context is you want them to go to bed, and you want to answer their why in some sort of way. What are you going to respond when they say why?
Because I told you so.
Because I told you so. Okay, that's the first kind of response. That is called authority. You're asserting authority. You're saying, because I told you so. There's no why of that. Right? That's the end of the conversation. Right? Here it is, the rule, because I told you so. Okay. What's an alternative? Yeah.
If you don't go to sleep, then you'll be tired and you'll go down.
And what might the young person say in response to that?
I don't want to go to school.
Yeah, or why do I have to go to school? Or, some further why. And what might you say in response to why do I have to go to school?
Because you need an education.
And what might the young person say in response to, because you're going to get an education? Why do I need an education? Okay. And then you could say in response to why do I need an education? Well, because it's going to allow you to make money when you grow up. And the young person, they might say, why do I need to make money? Then you might say, well, because you need money to be able to buy food to eat. And the child might say, Why do I need to eat? Okay, why will I die? What? So you kind of have a choice here, and we're kind of getting into this. At some point, you could assert authority, like Ashley started us off. Or you could just keep going, and you could keep going forever. And if you kept going forever, you imagine like a stair step where each Y is like another step in the stair, and you just kept answering them forever, 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 forever. That's called infinite regression. At some point, you might say, wait, there's an answer to that, but I'm done for right now. Let's take a break, and I'll get back to it. Right? But you have in your head the sense that that set of reasons just goes on forever. Does everybody get how that feels kind of different from the authority example? It's not saying, because I said so at any point. It's just leaving open that the chain of reasoning is going to go on forever. There's another one. Sam started us with, so you can get to school in the morning. Child says, why do I want to get to school in the morning? Ashley says, so you can get an education. Why do I want an education? What if instead you kind of pull a little bit of a trick and you say, so you can go to school in the morning? You kind of set up this circle, and it's like, wait. So the reason that I'm going to go to school in the morning is to get an education. The reason I'm going to get an education is so I can go to school. Why am I going to go to school? So I can get an education. Why am I going to get an education? So I can go to school. Right? And it becomes this circle. Right? That's another way that you can deal with it. Right? Then it doesn't keep going anymore. It stops right at that circle, and that circle just repeats. Right? That's called circular reasoning. And those are really the three. Now, somebody in my previous period said, well, wait, what if you just say kind of get experience in the world? And that's kind of an alternative thing. It's no longer in the realm of giving reasons. It's no longer in the realm of explaining why. That's kind of inductive logic, where instead of building on top of a set of reasons, you are asserting or allowing experience to be a guide. And if experience is a guide, and if the child says, you just say, well, don't go to bed then, and the child just stays up, and maybe they're tired the next day, and then they learn based on that experience, you're allowing, if that's kind of the way that you're doing things, you're allowing for the situation to be like different for each person. For the child to say, well, you know what, I didn't actually feel tired the next day, or I got good sleep at school the next day, and I don't actually need to go to bed early. I'm going to stay up late every day. Right? And you have to be ready for that possibility. It's not necessarily the wrong way to deal with a question. So I want everybody to feel right now that this sense of we're navigating the very most basic question of why anything is true. There's kind of that learn from experience and generalize that experience, not through a rule of something that must happen every time, but kind of just a generalization. Or three different possible ways to take strict reasoning and to start it out. And then here's the question, which one of those three ways does math start? Because math does use those strict reasons, but how does it start everything out? Infinite regression, circular reasoning, or authority? Authority. It starts it all out with authority. What do we call that authority?
Axioms.
Axioms. And there we go. Right? And I don't want to leap right into the axioms. I got another metaphor for you. Right? The axioms don't necessarily feel the authority that mathematics use, in my experience, doesn't feel the same as a parent saying, because I said so. It feels a lot more like the scenario of you being a little kid on the playground. And do you remember playing on a playground in your life ever? So you remember being like on a playground and like maybe a kid invents a game. Like a kid says, wait, all the wood chips are lava. When a kid says that, if you would respond to him by saying, oh, no, it's not lava. Look, I'm walking right on it. It's not hot at all. Like, what's going on there? I mean, what's happening? Yeah, describe that situation where you do that. Like, are you playing the game? No, you're kind of opting out of the game. You're saying, I'm not going to play that game. And that's a valid choice. You don't have to play anybody's game. But if you play the game, then you got to just kind of go with the floor is lava. And maybe you can throw your own rule into the game. You could say, there's no gravity. And then you're like jumping and like, if you're saying, wait, you just jumped like this high off the ground, then the other people aren't kind of going with that game. Right, there's no law, there's no gravity. You're supposed to be able to jump all the way up through the clouds, right? And maybe you caught like a fish in the clouds or something, right? And you can kind of make up these rules. And now, can anybody say, you know what, the lava game is the right game to play, and the no gravity game is the wrong game to play? Well, I mean, somebody can say it, but they don't really have any ground to stand on, right? Like I could say, I don't like the lava game, but I can't really, in any coherent way, say that the lava game is the wrong game. I mean, it's all about having fun. That's what the authority in math, that's what the axioms in math feel like. You get to pick this. Like you've probably in your geometry classes heard about the parallel postulate, and how the parallel postulate is a particular postulate in geometry that Euclid, a famous old dead white guy who's given an overabundance of credit for kind of inventing geometry, who really just wrote a book that brought together a lot of ideas that a lot of people had put together over centuries. He kind of accepted this parallel postulate. And if we don't accept that parallel postulate, if we don't play by that rule, we end up with another kind of geometry that's referred to as non-Euclidean geometry that's also pretty cool. It's a cool game to play too. And how do you pick which game you want to play? Well, you just kind of talk and you say like, this game looks like, let's play this one. This one looks more fun for this particular situation. This one looks more fun for this situation. Okay, and yesterday we started listing out some of the rules that we were going to play in our game. Let's list them out today, and we have to finish the list. I don't think we managed to finish the list yesterday. I can't remember how many we got to. Our axioms. Nathan, you got any of them? You remember any of them? Any of the axioms from yesterday? Yeah. Do you remember any of them? Sam? Yeah, you Nathan. Right? Say it louder. No, that was, so what you're remembering is the work that we did yesterday to distribute these. After we did this work, we did talk about a couple of axioms. Yeah, Alex. The commutative property. Remember this? Yeah, commutative property. What kind of commutative properties did we have? Addition and multiplication. addition was A plus B is the same thing as B plus A. And we decided we wanted to play with that rule. And multiplication is A times B equals B times A. Anybody come up with, or anybody remember the other one that we did, Sam? Distributive property. And can you tell me, Sam, what the distributive property says?
A times B plus B equals AB plus BC.
Okay. And I don't think we did the last two. I told you there were going to be 5 rules. I don't think we got to the last 2. I heard somebody say it as they left. Yes, go, Adam. That was you. The associative property. Did you figure out last night what the associative property tells you? Does anybody remember now seeing the word associative property, what that tells you? There's 2 associative properties. Yeah.
Like A plus A equals 2A.
So you're talking addition, so I'm going to write that down. The 2 associative properties of the associative property of addition and multiplication. And you said, say it again?
Said A plus A equals 2A.
A plus A equals 2A. So figuring out that A plus A equals 2A, that's actually, it's like combining like terms. And that actually comes from the distributive property. And I think we're going to have time for this. If we run out of time, tell me that I made a mistake when I did this. I'll go back and edit the video, pretend it never happened. But A plus A equals 2A. Can we use the distributive property to show that's true? Well, does anybody have any ideas? How can the distributive property allow us to combine those like terms? What can I do? How can I match this A plus A up with the distributive property? Would I match it up with the right or the left-hand side? So I'm trying to go from here to get to here. How can I go from here, A plus A, to get to there? First of all, this A plus A. Is this going to match up with the left-hand side or the right-hand side of the distributive property? The right-hand side. There's no parentheses, so it's got to match up with the right-hand side. It's a little tricky here because we don't have like the form of this A plus A. If I write right above it that AB plus AC, it's not clear what my B and C are going to be. Does anybody have a thought on what my B and C could be? Yeah.
It'd be 1.
It'd be 1. Yeah, I'm thinking of A as A times 1. And this is actually, it raises the question as to, raises the question of how do you know that A times 1 is equal to A? That's really, so I'm going to rewrite A as A times 1. And then the second A I'm going to write as A times 1. That's actually something called the multiplicative identity, or the property of the multiplicative identity. When you multiply anything by 1, you get the thing. So A times 1 is the same as A times 1 is the same as A. And now we can really match this up. So I'm going to move this over to here. And now we see we've got, this is supposed to be plus. Oh my gosh. A plus A times 1 plus A times 1. We're matching up the A times B plus A times C, and B is 1 and C is 1, and A's stay the same. The blue A doesn't necessarily have to be the same as the black A. What we're capturing here with this is position. What this is showing is that we've got a thing out in front of parentheses with 2 things being added inside the parentheses. That's the same as the first thing times the first thing inside the parentheses plus the thing outside the parentheses times the second thing inside the parentheses. Right? That's what it's showing. And we can use this in either direction. So we can go backwards from there to there. So we know that this is the same as A times B plus C. What was A again? What was I matching this blue A up with again? Look at this blue A. It's the same as this blue A here and this blue A here. What are they matched up with? Actually just matched up with the A's. So the blue A is the same as the black A. And what's the B matched up with? The B is matched up with 1. And what about the C? 1 as well. Okay. So now I'm just going to write this, but where there's the blue A, I'm going to write the black A. And where's a blue B, I'm going to write a 1. And where there's a blue C, I'm going to write a 1 as well. And then I add those together. 1 plus 1, and I get 2. And I get A times 2, which is not the same as this. How would I show that A times 2 is the same as 2A? Do I have any rules over in my list here that would show me that those are the same? Do I have any rules in my game that allow me to assert that? Yeah, the commutative property. Which one? Of multiplication. I'm multiplying so that I can change them like that. So the logic of this proof, and a lot of the proofs will look like this, and you won't have to actually write for each of the equal signs. I'm not so worried about you memorizing these words, right? I'm worried about you. My objective is for you to understand the reasoning. And this is a good example of what a typical proof in here would look like. Right, we're going to do over on this board a much more formal, much more careful proof, and it'll be our first kind of careful formal proof, and we'll write why each of the equal signs is true. But this is a reasonable argument that A plus A equals 2 times A. And you can think about each of the equal signs and see why it's true. Again, this first equal sign is true because when you multiply something by 1, you get the thing. And we're just using that backwards. The second equal sign is true because of the distributive property. The third equal sign is true because 1 plus 1 equals 2. That's a little tricky. Like, why is that true? Why is 1 plus 1 equal 2? I don't know. I'm not going to go too far into that. That's going to be basically an axiom as well. And then this last equal sign is true because of the commutative property. We can change the order. A times 2 is the same as 2 times A. In other words, A plus A equals 2A is not the associative property of addition. It is a result of the distributive property and the commutative property of multiplication. As would be the case for any time you combine like terms, like 5x plus 3x, which we saw in all our examples yesterday. I'll just tell you. The associative property of addition says this, that when you have two things being added together to a third thing, A plus B, the quantity A plus B added to C, that's the same as A added to the sum of B and C. Right? This first, the left-hand side is saying, take the two numbers, the first two numbers, add them together, then add the third number. This is saying, take the second and third number, add them together, then take the first number and add it to those two. The multiplication one is really similar. A times B, in parentheses times C, is the same as A times B times C. And those are our 5 basic rules that we're going to use for playing a lot of the games that we play. One more setup piece before we do it. We looked at x plus 3 times x plus 7. Oh, I have my glasses. X plus 3 times x plus 7. And we distributed the first terms, x times x, and got x squared. The outer terms, x times 7, and got 7x. The inner terms, 3 times x, and got 3x. And the last terms, 3 times 7, and got 21. We also did this problem here, x minus 1, x minus 6. And we distributed the first terms, x times x, and got x squared. Then the outer terms, x times negative 6, and got negative 6x. The inner terms, negative 1 times x, and got negative x. And the last terms, negative 1 times negative 6, and got plus 6. When we went from here to here, did we know that we could do that? Had we proven that you're allowed to just do that, take those first terms and multiply them together? No, we hadn't proven that at that point. That's what we want to do now. If I prove that you could go from here to get this, it wouldn't also prove that you could go from here to get this. Right? We're not using, when I say prove, we're not going from here to here based on anything over here. There's no rule over here that says that you can do this, that you can go exactly from here to here. There's no rule that says that. Nothing here says in one step that you could go directly from here to here. There's no rule that says you could go directly from here to here. So we want to kind of come up with a general statement. We want to come up with a general statement that would, if we prove that one general statement, that would allow us to say, well, you can go from here to here, and you can go from here to here because of that general statement. And we're going to call that the Foil Theorem. Right? It's a conjecture right now. A conjecture means something that you think you're going to be able to prove, but you haven't proven yet. A fact that you think is true, and you think you can prove it's true based on the rules that you're using in your game, but that you haven't proven. Once you prove it, it changes from a conjecture to a theorem. I see, Ashley. Can anybody think, including you, Ashley, of a way that I could state this so I could prove it one time and then not have to prove it for this and prove it for this and prove it for all the other examples that I can come up with?
I was thinking maybe like an inverse proof of FOIL. So it's like if you take it from one side, you can take it to the other side, from that side, you can take it to the other side.
I like that, and that's actually important. So what your homework is all about is about going the other way. It's about going from here to here, right? Factoring, it's called. And we're going to do that, but your homework, good time to mention it, your homework is not going to be due tomorrow. It's going to be due on Monday, because we're not going to have time to go over factoring, and I wanted to do a little bit of it before I give you the homework. Maybe I'm going to regret that. No, I said it. I'm not going to go back on it. Okay. Fourth problem that we did. This is going to be our conjecture. That's a weird scene. I'm going to start with this. Can anybody explain why does this cover both of those cases and a whole bunch more? Like, what is this kind of template showing? What do we have here in its most basic essence? Yeah.
Variable represent all numbers.
Yeah, so like in the first set of parentheses, we have two expressions being added together. And in the second set of parentheses, we have another two expressions being added together. And I could match this up with this right here. What would A be? And what would B be? Careful. -1. And what would C be? And what would D be? Okay, and what about this one? A is, B is, C is, and D is, right? So you see that you can match it up. So if we can prove this, and what did we want to prove about this? Well, we want to prove FOIL, right? That you can take the first two values in the two binomials, the first value in the first binomial A and the first value in the second binomial C, multiply those together. Take the outer terms in the two binomials, the A and the D, and multiply those together. Take the inner terms in the two binomials and multiply those together. And take the last terms in the two binomials, B times D, and multiply those. So that we have first, outer, inner, last. Okay, so now we got to try and prove this. This is what you would need to generate on the test. We have a choice. When we're proving an equal sign like this, we can start with the left-hand side and get to the right, or we can start with the right and get to the left. There's usually, in a lot of proofs, one of those ways is going to be easier than the other. Which one of the ways, in your experience, is easier? Going from where you have things in parentheses and getting rid of the parentheses, or going from no parentheses to having parentheses? Factoring or distributing? Distributing, going from here to here. And we're going to find that proving it is easier that way as well. There's a really important mathematical practice standard called make sense of generalities from repeated reasoning. I'm misquoting it. It's something close to that. But the idea is repeated reasoning, doing a bunch of problems over and over, you start to see the general truth. And that's why we started with doing a bunch of examples like this. And we're going to take the examples that we did like this, and now we're going to do them like this. But we're going to be really careful, and every single step is going to be exactly one of the 5 options from our list of rules. So let's start with this here. And does anybody have, I put that in slightly the wrong place. Does anybody have an opinion as to, and to make sure I get a lot of voices, everybody's going to get at most one line. So like we're going to do a line. We're going to say this is equal to something. So whoever tells me what it's equal to, what property we're going to use here, you're going to talk me through the line, but then you're kind of done and give somebody else a chance. Okay, so anybody have a choice? What do we start with? What can I match that up with? Which out of these can I match it up with? Chelsea says the distributive property. Can you explain? First of all, Chelsea, do you want me to match it up with the left-hand side of the distributive property or the right-hand side of the distributive property? The left. You want me to match it up with the left. Okay, so I'm going to write the left-hand side up above here. And I want you to tell me, what do I match that A up with from the distributive property? What do I match it up with here in this expression? You want me to match it with the B? Wait, so I'm going to take this A right here and match it up with something over here. So, you know what? A way to think about the distributive property is it takes something out in front of some parentheses that contain a sum and allows you to take the something that's out in front and distribute it to the first thing inside the parentheses and then distribute it to the second thing inside the parentheses. So you've got to figure out what do we match this A up with? What's the thing that's out in front of parentheses? And feel free to toss Chelsea like a assist here. What can you match up with that?
What was the question again?
So we're trying to match up this A times B plus C, this, with something over here. And you've got to match it up, and it's got to be kind of a perfect fit, basically. Justin, you want to throw?
A plus B.
You want me to match the A plus B up with the A. Okay, let's see if that works. So I'm matching the A up with the A plus B. And then what do you want me to match the B plus C up with? What should the B match up with? Do you want to go back, Chelsea, and you take over again? Do you want to stick with it, Justin? What are you going to match the B up with now?
C.
What if we match the B with the C? Okay, and what about the D?
C.
Okay. So it's a little, there's like a lot of different ways to show this. I'm going to try to show it with my hand. Right, my hand is the A. So here, my left hand is the A. Look at what's happening with the A here. What happens with the A? Well, it distributes to the B, so we get A times B, right? And that's right there, A times B, right? And then the A distributes to the C, and we get A times C, right? In this case, what Justin just guided us to do is to take the A plus B, and that's our A. And what are we going to distribute it to? Well, we're going to distribute it to the C. So what are we going to write over here? Right? What's pause for a minute. What's this equal to according to the distributive property? A times plus A times C, right? That's just the distributive property. I just copied, this is just word for word, or letter for letter, symbol for symbol, copied from over here, right? Okay, let's just do it this way at first. What was the A? What did we map the green A to? To the black A plus B. What did we map the green B to? To C. So I've got A times B. The green A was A plus B. The green B was C. A plus B times C. Then we have our plus sign. What was the green A again?
A plus B.
A plus B. And what was the green C? Okay, let's look at that again. Using my hand as the A. So my hand is the A. So like if it was up here on the distributive property, the A distributes to the B, the A distributes to the C. When it distributes to the B, you get the A times B. When it distributes to the C, you get the A times C. Here we're going to take that A plus B is the A. That's the thing that's distributing. We're distributing it to the C. So this whole thing that's distributing multiplies by this. That's exactly what's written right there, right? The A plus B multiplies by the C. The A plus B distributes, multiplies by the D. Right, let me, everybody kind of see that in their mind's eye? We got that A plus B and it's distributing to the C. A plus B times C. A plus B distributing to the D. A plus B times D. That's a direct application of the distributive property. All we did was match this left side up with the left side of our conjecture. And then we applied the distributive properties. And we can say this equal sign is true. Why? Because of the distributive property. All I'm doing is following the rules of what the distributive property says. When you have an expression out in front of the parentheses, you can distribute it inside the parentheses. The thing out in front of the parentheses is A plus B. The thing inside the parentheses is C plus D. So I'm distributing A plus B to the C and then to the D. Are we done? Is this the same as this? No, it's not the same. So what I'm going to do, and you really don't need to do this usually when you're doing a proof, but it can be helpful when we're learning it, is I'm just going to copy over exactly what we got. And I'm going to ask, what can we do to this to get closer to this? Bianca?
Maybe we could use the associative property and multiplication.
So if we're going to use the associative property of multiplication, we have to look at it carefully And note, if you're kind of like squinting your eyes, like looking askance at this, or looking like from a distance at this, what does this say? Well, it says you got a thing times a thing, inside parentheses, times another thing. Do we have that over there? See if you can find anywhere where we have a thing times a thing, inside parentheses times another thing. We don't. We have a thing plus a thing, inside parentheses times a thing, but that isn't quite the same. I can't decide. Sam. Commutative property of multiplication. Did anybody think, you know what's going on here? When I look at this and I look at this, I say to myself, well, this has parentheses and there's no parentheses up here, right? I need to get rid of those parentheses. Did anybody think I want to use the distributive property at this point? Like if you were doing this and you were just trying to get to this, wouldn't you distribute the C and the D? Can you use the distributive property? What does the distributive property say on the left-hand side? What do we have? Remember, we have a thing out in front of parentheses times two things being added together inside parentheses. Is that what we have here? No. That C's in the wrong place. Sam saw forward. He realized, wait. That's not going to work. I can't distribute that C. Or could I move the C to the front so that it would be in the front? What allows me to do that, to move the C to the front? Because a commutative property of multiplication or addition? Multiplication, because what's happening here is we've got this thing with the parentheses being multiplied by C, and we want to do it in the other order, right? When I take my commutative property of multiplication, right? I'm going to take this A times B. What am I going to match the A and the B up with? What am I going to match the A up with one at a time? Yeah, Sam, this is your line, so finish it for us.
A is the A plus B.
Kind of like above, we're going to match that A plus B up with A. And then we have A times B. What's the B? Oh, then we just changed it. Okay. So let me write that down before we go on. So instead of A plus B, I'm going to write, tell me what to write here.
C, and then in parentheses A plus B.
A good trick for saying that is C times the quantity A plus B. Awesome. And then I just write the rest the same?
No, you do the commutative again.
Oh, because the D needs to be in front of the parentheses as well. So I'm going to change the order there. I'm going to use this exact same property, right? Where I'm going to take the A plus B and the D, and I'm going to change those around. And what do I get?
Yeah, D times the quantity A plus B.
And why is that true?
That's true because we commutative property.
Okay, are we done now? Yeah, Ashley.
I had a question, so
Yeah.
what makes the difference of it being in the front and then it being in the back?
Well, because this says that all it says is that you can exactly take something in the front of the parentheses and multiply it by the first thing in the parentheses and then by the second thing in the parentheses. Right? And so we have to match that exactly. And I think Ashley's guiding us now to what our next step is going to be. Just slight explanation. I would love to keep going at the pace that we're going, but I'm aware of the time, and we have time to finish it, and I want to finish it because I think it's going to be helpful, right? Ashley's saying, oh, well, now we've got our C in the front of the parentheses, our D in the front of the parentheses. What can I do now? Distribute. I'm going to take the C and distribute it to the A and the B, right? So this is really, this C times A plus B is just like the A times B plus C, right? Where the A is the C, the green A is the black C, the green B is the black A, and the green C is the black B, right? And I can distribute that to get C times A plus C times B. Now do the same thing with the D, distribute the D. D times A plus D times B. Okay, I must be done, right? This is exactly the same as this. Now that I use the distributive property, those are exactly the same? No, they're still not. Oh my gosh. What's wrong with them now? This says AC. What does this say? CA. Could I change the order? Why? Commutative property of multiplication again. Change the order. AC plus B. I have to do all of them actually. CB here. It's actually BC here. Okay, so one more step and then we're done. AD plus BD, right? Commutative property of multiplication, and they're identical. Right? Everybody's learned my voice. You know that they're not identical. Why aren't they identical? What's different between these two, and between this expression and this expression? Say it louder, Adam. Oh, was that Alex? I'm sorry, Alex. Say it. BC and AD are in different order. This is BC plus AD. This is AD plus BC. Well, that's the same thing, but why is it the same thing? How do you know it's the same thing? Of what? Addition. Alex is telling me take this BC plus AD and write it the other way around, AD plus BC. So I'm going to write this over and I'm going to change that one thing, AC plus AD plus BC plus BD, commutative property of addition. And as a bonus in the last few seconds, you get to put QED, which means quad errata demonstratum, which stands for quad errata demonstratum, which means it has been shown. Or you could put a little box, that's kind of cool, or even just like more kind of subtle and non like glaring, you could just put a check mark. We finished our first proof. And that's 24 points if you could do it on the next test. Have a great lunch, everyone. Sorry, we went 20 seconds over.